for the YouTube as well on the lecture. With the essay you're writing, as well as showing how well you understand the concepts and how well you write, which is important, one of the things about this being a very first reference is we want you to see that you can do the referencing you need to do for an academic paper. And the basic idea of the referencing is you have read a reference, you found something which is useful for the essay you're writing, and you want to show that's in the text. So you write the author, the year the paper came from or the book came from, was written, and the page reference. That's the basic story. So to show you, like with one of my academic papers, which I'm waiting for word back on a journal on this one, as part of it, I make a reference to a guy called Robert Solow and what he called the smell test. And in making that statement, I reference the page of the reference on which that occurs. So you write the author, the year, the page reference, and then in the bibliography, there I have what I'm actually referring to as this particular entry here. Okay? So there's two parts to it. One is where you've used an idea from someone or you've used a quote from a paper. You write the year, the author, the year, and the page reference. And then in the bibliography, you provide the author and all the details of where it came from. So it's just showing the author, the year, the title of the paper, and where it was presented. And if you want to use that for ICAT, this is the university's online system. Let's imagine now we're looking at, say, you want to have a comment on Austrian economics and budget deficits, for example. Then ICAT is an intelligent search system. It'll bring up a range of articles here. And for example, let's see, what is this one? Finance and economics. Okay. The strong increase in Austrian government debt. That's not what I want. Can the Stability and Growth Pact cause budget deficit cycles? That might be relevant, for example. Let's imagine that's an Austrian economist commenting on what's going to happen with budget deficits in Europe, courtesy of the Maastricht Treaty. And then what you get, here's the reference. You can actually get the actual text by clicking on this link. I'll just open that in a new tab. So that brings up the article, and you could download the article and read it, which is part of what you're doing for research. But in referencing it, you get a range of elements here. You can export to programs that do the formatting for you and insert that into the Word document. That's what we'd like you to learn over time. But for example, if I click on citation here, then there's the text, and I can simply copy that and paste that into the article I'm writing. I'll make that larger so you can see it on screen. Okay, so there's the text, and let's go and take a look at it. And that's what you'd need to put in the bibliography. And then if you refer to that article, you'd say Huell and Suter, the two names, 2003, and say it was on page 28, comma, page 28, or colon 28, which we read the same way, okay? So that's something we expect you to do as part of the referencing. Now, even if you relied mainly on online sources to write your essay, make sure you include 2 or 3 bibliographic references as well. Read a journal article, read part of a book, and then put that inside there, and that'll just have the person's marking the essay, maybe me, maybe somebody else, might be Hermione, say, okay, yes, well, you've shown you can actually do formal citations and do a formal bibliography, okay? Now, let's get to the lecture itself today, and what I'm talking about is something which is ways in which I think all schools of thought, and that is they don't handle the environment properly. So I spoke about the post-Keynesians last week and how they differ on not having a theory of value. They also focus, like the Austrians do, on limited knowledge and uncertainty and so on. But now what I want to talk about today is the environment, and how does economics handle the environment? Does it properly think about it? Now, did you see who the Nobel Prize was announced last week in Stockholm, the Nobel Prize for Economics? Okay. One of the guys who got the Nobel Prize, I think, has done a lot to scuttle how economists think about the economy, about the ecology, a guy called William Nordhaus. So I'm going to be awarding him what I call the Nobel Prize next year with a bit of luck. But economists don't understand the ecology, and the way you're taught to think about the ecology as an economist, I think, is highly misleading. So I want to show what I think a proper reformation of economics might do to consider how the economy and the ecology interact. And it's quite difficult. I remember actually the student who asked me the question, what's this got to do with economics? In the first lecture I was talking about astronomy. If she were here, she'd be saying the same thing about this lecture, but you'll see where it comes down to the interaction with economics after that. So let's take a look at it. Now, as I mentioned, when I gave the first lecture, I talked about blind spots, that because you ask a particular question about the economy, you don't think about other ways to understand it. And that's the common situation. One school has a blind spot. That happens to be a focus of another school. In ecological economics, they've all had a blind spot about it, unfortunately. And this is, again, those students I showed you from the Netherlands who are challenging their professor. They made this point as well about blind spots. So I'll just let this one run once the YouTube link downloads. Got to wait. If I click too early, I'll click and I'll go back to it. Here we go. Okay. So he says, let's see. You get tunnel vision, but economics is diverse, and they talk about 9 theoretical schools, which is more than I'm covering for you, but I'm covering the main ones here. Their own perspectives on the economy and their own blind spots. Okay. Now, this particular point is shared blind spots. On the environment, I think, is the most important one. So each school will attempt to address the ecology from the point of view of how they think about the economy itself. So the neoclassicals will think we have pollution, and the reason we have pollution is price signals aren't right. Pollution is something which people dump in the environment and don't have to pay for, and therefore there's too much of it. So what we need to do is get a price on carbon, for example, and that'll reduce the amount of waste, and that's the solution to the problem. That's how they think about it. Now, the Austrians think, well, the fact that nobody actually owns the environment's the problem, because if anybody owned the environment, they'd be charging you for the right to dump waste into the environment. So what we need to do is enforce property rights. We have to give people rights to the air over a city, or rights to the to a river and a lake, and then they'll police those property rights themselves, and that'll solve the problem. Post Keynesians say, well, they admit we haven't done a good job. Okay. We haven't integrated the ecology into the way we think about the economy, and that's bad. But they'll say it's going to be a complicated solution, but given the scale of the problem we face, the state will probably have to play a leading role, because it's unlikely anybody's going to make a profit out of solving global warming. Okay? Who do you reckon will pay for refreezing Antarctica, for example, if we happen to melt the place? It's just not going to happen. So they're saying we need to mobilise resources, and most likely the state will do that rather than the market system. So that's the 3 broad ways of the way they look at the ecology from their own points of view, but they still, to some extent, realise that it's inadequate. Now, there's now a school of ecological economics, and I haven't covered that at all in these lectures because of time constraints, but to talk about their views, they say there's been 100 years or more, 200 years, of us specialising in trying to analyse the economy, but we still don't understand how the economy interacts with the ecology. So they're saying this is a major issue, and ecological economists are trying to find a solution to understand that particular vital aspect of the economy. But it's a minority school. There's less ecological economists than there are post-Keynesian economists, let alone neoclassical economists. So only a tiny amount of doing work on it. They only get a tiny amount of funding. So there's been very little progress in that absolutely essential area. Now, why do they find it so hard to think about the environment? Well, I think it's because they start from the mainstream point of view, the neoclassical point of view, that trivialises the economy because of concepts like perfect competition. And you'll be getting this in your micro course. And the idea of what they call the circular flow. So these are concepts that once you have them in your head, they tend to structure how you think about the economy. And there's very little that's covered about the economy, the ecology, and other theories as well. So if you have the idea of perfect competition, that implies that you can have zero waste. If you look at how perfect competition is shown, you have the idea of a graph quantity being sold on the horizontal axis, the price being charged on the vertical, downward sloping demand curve, upward sloping supply curve. The equilibrium price is what's supposed to be what things are sold at. Everything above that line gives you the amount that consumers are gaining out of the market. Everything below that line tells you what producers are gaining out of the market. And there's no waste. Okay? No dead weight loss. You'll see that concept being used all the time when you look in your micro courses both this year and in future years. Again, if you look at how they describe what they call the circular flow, that treats the economy in complete isolation from the environment. So here are some sample circular flow diagrams. I think this is from Mankiw. And here you have product markets, goods and services, factor markets and firms. And notice there's jeans and haircuts and apartments all shown with intersecting supply and demand curves. And factor markets, workers of different sorts, households. There's no mention of the environment there. Here's another one. This has factor payments, or firms making payments to what they call factors, which are going to be both labour and capital, going to households who then consume, and there's sales receipts. They've got government inside here and financial institutions and so on. But there's no mention of the environment again. So you get trained, even though you're not conscious of it, to think you can think about the economy without thinking about the environment. There's no, notice in both those diagrams, there's no input from outside the economy. Nothing that wasn't produced by the economy itself. So here we have product markets, firms reducing output, selling it to workers. There's nothing actually being taken from the ecology itself. And it implies that a system like that, which doesn't have any interaction with the ecology, can produce output over time, and that's just not possible. That is simply logically wrong to imagine you can produce anything without taking in non-produced stuff like land and solar energy. Nobody makes the land. Nobody makes the sun. But without those two, we couldn't do anything at all. We wouldn't exist. And it also applies you can have production without dumping any waste out of the system. That's also wrong. So I wanted to explain to you why those things are wrong. So the circular flow, the whole idea that we can continue producing and consuming, comes out of the fact that we're exploiting existing energy that we didn't create. Humans did not create the sun. Humans did not create the coal that's stored solar energy over time. We just found it. And nuclear energy the same. So one of the rules of physics is you can't produce energy. Energy simply exists. And the amount of energy doesn't change. Its form changes. It might go from being like light radiation, so we're seeing light radiation so that we can see what's happening in this room. But that gets converted to heat. When those things bounce off us and there's reflection, part of that is reflected heat. That's so the first law of thermodynamics is you can't make energy. We can only exploit energy that already exists, and that includes converting matter into energy. So even E equals mc squared is saying we're taking matter and converting it to energy, but it starts as a form of energy in its own right. And when we do that, we necessarily generate waste. You can minimize waste, but you can't get rid of it. You cannot eliminate waste. And those are the second and third laws of thermodynamics. Now, so we're going to make the circular flow diagram realistic when talking about this absolutely essential role of what we find for free, the ecology. We have to have energy inputs, which are coming from the non-man-made environment, and we have to have waste injected back into that environment. Then that's the minimum possible to make that diagram realistic. So if you look at the idea here, you have the sun generating energy, which lands on the planet. We exploit some of that energy to do useful work, but part of it also necessarily gets converted into waste, and that gets dumped into the environment as well. That's the absolute minimum to make this work. So, but I need to explain why you can't produce anything without using existing energy, and why we can't produce anything without creating waste at the same time. And this involves what's called the laws of thermodynamics. If any of your friends are doing a science degree, engineering degree, they'd be learning this in the first couple of lectures. Economists normally never learn it. So me teaching about this now is quite unusual in economics. And these are empirically determined and absolutely true rules about the energy. Okay? There's no way you can get around these rules. They were discovered gradually by humans and finally formalised in the 19th century. And this was after neoclassical economics started to develop. So economists weren't necessarily exposed to this stuff when the basic theory you guys have learned was developed. And to really understand it, there's quite complicated mathematics. I keep on forgetting it. I've got to go back and teach myself it all the time. But I'll just give you a bit of a joke about it to try to explain it. This comes from you know the Big Bang show? The TV show called The Big Bang? It's one of my favourite elements of The Big Bang. Ah, right. Gotta wait for here we go. Now, where's my sound got to? Right. Okay, looks like it's not going to work in terms of sound. I'm not quite certain why. But that was, I've got Sheldon there trying to teach Penny physics. Here we go.
Research Journal, Entry 1. I'm about to embark on one of the great challenges of my scientific career. Teaching Penny physics. I'm calling it Project Gorilla.
Hey, Sheldon.
Come in. Take a seat. Subject has arrived. I've extended a friendly, casual greeting.
Ready to get started?
One moment. Subject appears well rested and enthusiastic. Apparently ignorance is bliss.
I think that pretty much summarises Economists. They're ignorant and blissful about the role of energy, and they've got no right to be.
Teaching Penny physics.
Okay. So let's just take a look at the joke versions of the laws of thermodynamics. And the first one is you can't win. Actually, there's what's called the zeroth law as well. You must play the game. Okay. The first law after that is you can't win the game. So why would you play a game you can't win? The second is not only can you not win, you can't even break even. So you're going to lose. Okay. The third rule is you can't leave the game. So what the hell does that mean? Well, you can't win, you can only break even. It says that you can convert energy from one form to another, but you can't make energy. Okay. So what you can do is take energy as it exists, convert it into some other form. You don't change the absolute amount of energy, you change its manifestation. So you might take solar energy, light coming in as we see it, and turn it into heat. Okay? But you can't create more energy than is coming in the first place. The second is, if you want to break even, then you have to have somewhere that you can dump your waste energy, which is at the temperature of absolute zero, which is 273 degrees below zero, as we describe. We talk about 0 degrees Celsius. Absolute zero is minus 273 degrees Celsius. And there's no such place. Okay. So you simply can't find somewhere to dump all the waste energy. Now, translating all this, you can't neither create nor destroy energy. You simply change its form. And the maximum amount of work you can actually do depends on being able to dump the waste that you generate into a background area. Like, for example, if you drove a car to get here, and you're dumping the waste heat from the energy that's being used by your car to transport you from home to here into the environment, you're dumping it to a background temperature of about 300 degrees above absolute zero, 280 degrees above absolute zero. And therefore you're wasting 280 degrees worth of energy. There's nothing you can do about it unless you can find somewhere that's so cold even England seems warm, and that's got to be at minus 270 degrees temperature. And we know there's no such place in the universe. That's one of the laws. So let's just take a look a bit more. What the hell am I talking about here? Well, if you're going to exploit energy, you have to have a gap between where the energy is and where you're going to dump it later. And the easiest way to imagine this is looking at a waterfall. And here's a waterfall. You can see water falling over the cliff and coming down and running past the wheel, which unfortunately isn't turning. But I noticed this and somebody sent me a little illustration what actually happens. So here's water falling onto a wheel and turning the wheel, and then the wheel can be used to do work. That's why you've got the wheel there, to convert that available energy into work. Now that can only happen if there's a gap between where the water starts and where the water ends. So if the waterfall was falling from this altitude to that altitude, there'd be no energy. The water wouldn't be moving at all. To get the water moving, you've got to have a drop between where it is and where it gets to. Now, the amount of energy you can exploit depends on how far the water's falling and how fast it's falling because it's falling. So in general, you need a gap between the temperature you're exploiting and the temperature you dump into. There has to be that potential gap between the two. Otherwise, you can't use the available potential energy to turn it into real work. So the waterfall can be a source of power if the height of the waterfall is greater than 0 metres. And the same idea applies in general. You can do work if the energy, the heat of the source you're using is greater than the background. That's the absolutely basic idea. So the original person who worked this out was a very young French mathematician called Carnot. I think he was only he may have even been in his teens when he worked this out. So he said you can do work if the source of the engine, the heat of the engine, is greater than where you dump the waste after you've exploited that heat. So you say it's got an engine. Imagine your engine is operating at 500 degrees Celsius. I have no idea whether that's a sensible level for a car engine. Does anybody know? Okay. We'll do a bit of a Google search and see what temperature a functional internal combustion engine works at. Let's say it's 500 degrees Celsius. And say the environment's, a warm day in Britain, 25 degrees Celsius. Then there's going to be a flow of heat from the engine to the environment, and there's a 475 degrees Celsius gap. That's the energy you can actually make use of. So you can harness that energy. Well, let's say we found ourselves on Venus with exactly the same engine. And let's say the background temperature of Venus is 500 degrees Celsius, which is that's a reasonable approximation to the ground temperature on Venus. The same engine wouldn't have any flow of heat because the engine would be running at the same temperature as the environment. There'd be no flow from one spot to another. So you can't harness energy if the background temperature is exactly the same as the temperature your engine works at. And it isn't, therefore, just how powerful an energy source is, which you measure by the heat that it can generate. It's how cold the surroundings are as well. You've got to have a gap. The engine you're using has to be hotter than the environment you're operating the engine in, otherwise it can't do work. So here's the heat of a source, and there's the sink you're dumping the waste into. That's your maximum usable energy. And that's the basic concept. If there's not a gap, you can't exploit the energy, even though it exists in the original source. So the maximum amount you can get out of a given source depends how cold the surroundings are. And what's the coldest surrounding temperature? Well, it happens to be minus 273.15 degrees Celsius. But we know there's nowhere in the universe that's cold. That's the third law. There is no place at absolute zero. Have you heard what's called the cosmic background radiation at all? Okay. I think it's about 2 or 3 degrees above absolute zero. That's the coldest we can find anywhere in the universe. There are colder spots, but there's various technical tricks about that. So the average temperature, that's the cosmic background radiation, 2.73 degrees above zero. So there's no way to exploit all the energy in any energy source, because even if we're doing stuff in outer space, we'd still have a temperature that meant a couple of degrees of energy to be wasted. So the average temperature of the Earth is about 16 degrees Celsius, which is 292 degrees above absolute zero. So that much of the energy that exists, we can't actually harness, so long as we continue producing on Earth. So any production source of energy, any mining system, any manufacturing system is wasting that much potential energy, and of course it dumps that into the environment. So if you have an ideal engine which has no friction, no leakages, its maximum efficiency must be less than 100%. Now you compare that to the vision of perfect competition. It implies you can have a market with 100% efficient. So economists are working with this idea of potential for 100% efficiency. Engineers know that's not possible. Who's more realistic? It's the engineers. There's your heat of the source, which I'm calling S. There's the heat of where you're dumping the waste, which I'm calling D. The maximum amount of work you can do is 1 minus D divided by S. That's your maximum possible efficiency. Now, if your dump is zero, absolute zero, then you can turn all the available energy into work. But your dump happens to be, in the case of the planet Earth, roughly 300. So no matter how much energy your source has got, you're going to be still wasting 300 degrees of temperature. With a car engine, as I was showing you before, you might get 60%, 70% efficiency out of it, measuring from absolute zero. So if you had, say, 1,000 for the car engine, and that's measuring now in Kelvin degrees, when you do this sort of calculation, you work from absolute zero, not from the Celsius zero, which is the freezing point of water. So that might be, an engine might be operating at 1,000 degrees Celsius, Kelvin, which is 1,000 degrees above absolute zero. It might be 300 degrees Kelvin outside. That would be a 27-degree day, pretty warm for England, London. That's a big gap, but your maximum efficiency would be 70%. That's the best you can do with an engine with absolutely no problems from friction, leakages, etc., which of course is not possible. So we can approach this ideal, but we can't get there, and this ideal necessarily involves waste. So the whole idea of perfect efficiency is nonsense to an engineer. But it's built into how economists think when they talk about perfect competition, perfect knowledge, etc., etc. So we mislead ourselves that way. And the second law is where things get really complicated, because to actually take advantage of energy, you must be dumping waste into the environment. You have no choice. And this is why. Because unless you're exchanging the heat with an external system, you can't extract energy from it. If you have a closed system where there's no operation with the external environment, it cannot generate work. So look at power generation. This is a model from a engineering textbook, and I think you might see the model's already more complicated than anything you see in a normal economics textbook, because it's got the temperature of the water reservoir here, it's got the pressure level in kilopascals, it's got and I don't understand most of the terms here myself. I've got to go and learn them again. The megapascals for pressure, etc., etc. And it's got a boiler with a turbine. And notice the cooling tower is an essential part of the model. You see those cooling towers when you catch the train through the countryside, outside power stations? If the cooling tower wasn't there, the power station would produce no energy. And what's going on is that's where the generation of power occurs, because you dump the waste heat here. If you didn't dump the waste heat and you sealed the power unit, you'd produce nothing. Okay? That was completely isolated, then there'd be no energy production. I want to show you why. So here you have the boiler, and there's your turbine, and that comes back again after it's gone through the turbine. Now, the turbine won't spin if you close the whole thing off, because the temperature of the water coming out of the turbine would be the same as the temperature going into the turbine or the steam. So there'd be no movement. So to actually get movement, you've got to dump that waste, the gap here. You have to cool this bit down. So this comes in cold and this comes out hot. Unless this is coming hot, that's coming out cold, you're not going to turn the turbine. Okay? Now, this is what they talk about. This is one of the most complicated concepts in engineering, is what they call entropy. Has anybody heard of entropy before? Some of you have. Okay, most of you haven't. Now, when you look at, imagine I've got a cylinder and I've pushed a piston along, so I've compressed the air in one half and I've got close to a vacuum in the other. That is actually a very ordered state, because there's only a few arrangements of the molecules that give me most of the pressure over here and very little over there. So it takes energy to get to that situation in the first instance. If I freed that piston so it could move, then the pressure would push the piston. So it's an even distribution. And once it's in that even distribution, there's many, many ways that you can organise the atoms by moving different atoms around to get exactly the same outcome. This is a high probability that the atoms will be distributed this way. This is called high entropy. See, low entropy is organised. High entropy is disorganised. You can exploit energy when it's in the low entropy state. Once it gets to the high entropy, you can't exploit it anymore. And that's a universal tendency. We know the universe goes from a very organised state to a very disorganised state over time. Now, of course, our own experience, entropy is the level of organisation of something. So if you imagine like a raw material like iron ore, that compared to just dirt is more organised than dirt. Okay, but if I take the iron ore and then process that into steel, that's more organised still. So I'm going from high entropy to low entropy to produce something. But we know in the universe it tends to go from low entropy to high entropy. So we've got to reconcile these two. I'm glad you've turned up. I mentioned to you earlier, you asked the question about what's this got to do with economics. It's a similar thing happening now, talking about entropy and energy and how that's important to economics as well, but economists have ignored it. So my little analogy is this is a girl trying to make an excuse for a messy room. You can't fight the second law. Everything moves from a state of order to disorder. And that's a general rule for the environment without the intervention of intelligence or work. So, okay, what's this got to do with economics? Or question back in the first class. And two key things is you can't eliminate waste. You can reduce it, but you cannot eliminate it. So any vision that says we can use a carbon tax to get rid of carbon pollution, no, you cannot eliminate waste overall. So that gives you an immediate and unbreakable link between economics and the ecology. If you're going to do work, you're going to pump waste into the environment. No question about it. Okay? The only way not to put waste into the environment is not to do work in the first place. Okay? And there's no school of economic thought that covers that properly at the moment. Even the environmental economists haven't done enough work on that area. And secondly, you can't produce anything without energy. Energy is absolutely essential. And what's going with energy, with production, we're going in the opposite direction. We're taking stuff which is disorganised, so high entropy, and making it organised, which is low entropy. So we take the iron ore, we turn it into steel. Okay? Steel is much more organised than iron ore. Think about the metallic structure. And that is, how do we do that when the second law is an unbreakable law of reality? Well, overall, even though we're creating something as organised as steel out of iron ore, in the total process, we've got to be generating more waste, more disorder. So to take iron ore and convert it into steel, we have to be, at the same time, creating more disorder. So if you look at the iron ore and go to the steel, what you're ignoring is the slag, the waste, okay, that you generate. When you dig up the iron ore and dump it, when you process it, when you've got all the coal that you burn and the coke and so on, the sum total of all that stuff is more disorganised than what you started with. Otherwise, you're not going to be able to exploit that little bit. So there's an intimate link between production and waste. You cannot leave it out of your thinking. So this raises a whole range of curious questions, which again, economic theory hasn't answered properly. How do you produce a surplus? How do we produce more outputs and inputs every year? Which is what we do. And could we use market mechanisms to eliminate problems with the environment? Which is what a lot of economists think you can do. And can we grow forever on a finite planet? Which again, a lot of economists don't think there's a problem with production on a finite planet. And how do they produce a surplus, first of all? How do outputs exceed inputs and become more ordered, so from iron ore to steel? Well, you cannot produce a surplus if you're in an isolated environment. If you try to do all this with a locked door and not have any energy coming in and no waste going out, you'll produce nothing. That's the second law. Over time, that system would degrade. So the only reason you can produce is because the Earth is not a closed system. Every second of every day, we're getting enormous amounts of energy from the sun. If that wasn't coming in, we wouldn't exist, let alone be able to do work. So the incoming energy is absolutely crucial to understand why we can produce in the first place. And then if you think about, we talk about fossil fuels, the reason they're fossil fuels in the first place is that they absorb ancient energy, ancient sunlight. The animals ate the plants absorbed the sunlight. If that hadn't happened, they wouldn't be fuel in the first place. So in that sense, fossil fuels have stored energy, stored solar energy. Even when you look at nuclear fuels, the reason nuclear fuels exist is because a giant star, billions of years ago, exploded and created heavy elements, which that energy we can now exploit by fission, nuclear fission. But even that's come out of stars, much bigger stars than the sun. So what we've got with our farms and our factories, we're exploiting this free energy. And by free, I don't mean doesn't cost anything. I mean we didn't make it. It's been made for free for us by the universe, and we're exploiting it. And that's how we produce more outputs and inputs every year. But we necessarily, given that the laws of thermodynamics are completely unbreakable, okay, they're just total laws, okay? Like a speed limit you can break. The law of demand is always broken. You cannot break the laws of thermodynamics. So we must be creating more disorder than order. So the entropy, the disorder, has to be greater than the order we've created in the products we manufacture. So entropy exceeds the order of the original input. So if you looked at how disorganized, take the steel example, you've taken the iron ore, you've taken the coal, you've mined them, you've put them through a blast furnace, you've done all the processes to make it into highly refined steel. You record all the pollution you put into the air, all the carbon dioxide you've burnt in doing the process, all the slag you've created. Okay, you put it all together, you add up how organised is this versus what we started with, it's more disorganised. Okay. But we have a blind spot looking at this disorganised stuff. So let's look at the schools of thought and how well do they do in covering all this. And only one has ever been close to being correct, and it's one you would not normally learn about in any economics course, and that's a bunch of people called the Physiocrats. Now, they predate Adam Smith. In fact, when I'm writing my major book on economics, I'll be saying these guys were the real fathers of economics, and Adam Smith led us astray. Because writing back in 17th century and 18th century France, they were, in particular, a guy called Francois Quesnay, whom Adam Smith met, by the way, and borrowed some of his ideas, but also stuffed the ideas up. He was a doctor for the French king, and this is just after autopsies had discovered the human body had arteries and veins. We see all these cables running everywhere carrying fluids. Okay? So this idea of fluid flow became a vision of how the body operates, and Quesnay was fascinated by the economy as well, and he saw the same idea of a flow of fluids flowing from one organ to another. But he also, and this is a very important point, the Physiocrats, if you look at France when they were writing, France was much, much more agricultural than the UK was at the same time. The UK had started to industrialise, not with coal power at this stage, but with water power and so on, and animal power. And they, being much more agricultural, were seeing farmers would plant one seed and a plant containing 1,000 seeds would come up. Okay. Now, with that vision, they said, well, the only way this can happen is we're getting a free gift from nature, and that's what they literally called it. The husbandman, the farmer, is the only one whose industry produces more than the wages of his labour. He, therefore, is the only source of wealth. This is a direct quote, I think, from Cantillon. The soil, independent of any other man, pays him immediately the price of his toil. Nature grants a physical gift, effectively. Now, that's correct. That's the only written statement by an ancient economist which is correct about how we produce output. Okay? If it wasn't for that, we wouldn't make anything. The only mistake they made was they didn't think the industrial worker could do it either. But the industrial worker is working using energy coming from coal, which is stored solar energy. Okay? It's a longer-term process, but they're still exploiting energy. So what the Physiocrats said was, well, given that they thought only the farmers were exploiting this free gift of nature, they divided the world into three social classes. The productive class, which were agricultural workers, and they produced real wealth because they were mining this free gift of nature. And that's easy to see the surplus, because if you plant one seed, you get a whole plant back. Then they have what they call the sterile class, and that's industrial workers. And they thought they took what the agricultural workers produced, which was real value, and transformed it in some different form. It didn't actually increase the value. They weren't seeing the role of energy in what the industrial workers did. So they missed that particular clue. Then they had what they called the proprietor class, or the owners, and they were the ones who exploited, made the greatest wealth out of this because they were the owners. Now, they were wrong to think that agriculture was the only way you could harness that free gift. But they were right to say if you didn't get the free gift from nature, you couldn't do anything. So energy is absolutely essential to start the whole thing. Smith interacted with Quesnay and came back and wrote The Wealth of Nations. And rather than saying that land and the free gift of nature is the source of value, he said labour is the source of value. And that completely stuffed up economics for the next 200 years, in my opinion. And I'll be arguing that when I write my major book on economics. And then along come the Neoclassicals, who didn't like the labour theory of value, and they completely ignored where the surplus came from. So how do we actually make economics consistent with the laws of thermodynamics? Obviously, the air conditioning system is clicked in here. Talking of energy. Well, we're necessarily linked. If we're going to produce output on the planet, we must be dumping waste into the planet. That's absolutely unavoidable. Production necessarily requires energy, and you cannot substitute labour and capital for energy. Economists have this belief. They talk about flexibility in production, so you can substitute one input for another. So you could substitute labour for capital, and they would also think you can substitute labour for energy, which is simply not possible. You can, to some extent, you can use the energy in labour rather than the energy in machinery, but if you don't have energy at all, you can't produce anything, period. So they're quite wrong on this vision. And you can improve the efficiency of what we produce, but you can never get perfect efficiency. Then you say production is going to produce three types of outputs, not just what we look at in terms of goods, but the first thing is useful work. We're turning matter into something useful in terms of products or services. The second is waste energy, which we can't avoid. We can reduce it by being more efficient about how we make our machines, but we still can't avoid it, and waste products. So that slag that you produce, maybe you can find some other use for the slag, but ultimately there are some things you produce as a consequence of manufacturing which you simply can't get rid of and you can't sell to anybody else. So you get things like burning coal, you're necessarily going to make CO2 out of that. Maybe you can reduce some of your waste by, say, using 3D printing technology rather than using cutting tools to make machines. Let's try to visualise this, and we'll take a break at that point. So you're working inside an environment. This is where we are. We're on the biosphere. We haven't yet managed to get production off planet. We produce a surplus because free energy is coming in from the sun and from nuclear fuels and from fossil fuels, which are storing ancient solar energy. Useful work then powers the economy, and you need workers and machines to actually harness that energy to produce output. So there's the useful work. But because of the second laws of thermodynamics, we generate both physical and energy waste, which are necessarily dumped into the biosphere. So we get the combination, useful work and waste. And economics really must start from that point, and it doesn't yet start from that point. So it's one of the great weaknesses of all economic theories that we haven't properly understood how this thing functions. And then the problem we're facing right now is the biosphere, which of course includes the thin layer of atmosphere around our planet, slows how fast the waste we generate is transmitted back into outer space. So if we didn't have an atmosphere, if we were producing on the moon, for example, then the waste we generated on the moon, we could probably eject into outer space anyway. It wouldn't accumulate on the moon. It certainly wouldn't be slowed down by the moon's atmosphere in terms of radiating back into outer space because there is no atmosphere. So if you were having a production plant on the moon, particularly on the dark side of the moon, it'd be very, very cold over there. The waste it'd be less waste because of you're dumping into a cold background, and any waste there would be just transmitted as infrared radiation into outer space. But we're doing this on the planet. The biosphere has things like what are called global warming gases, the most important of which is actually water vapour, then carbon dioxide, then methane. Those gases, they slow down how fast that waste leaves the planet, the waste energy, and that then means that the biosphere's capacity to absorb and process the waste we generate actually degrades over time. And of course that can undermine the production process. If you're reducing the capacity of the planet to absorb the waste by dumping more waste into it than it's capable of handling, then over time its capacity to process that waste degrades, and we see the environmental problems we face on the planet. Okay, I'll leave you with that thought, take about 10 minutes and come back and go on for the second half. Now, and carry on the rest of the students, other students can arrive as they need. So, economics, as I said, is not consistent with the most important laws about the universe, which is ridiculous. So can we make it consistent? And I don't think we can make the neoclassical consistent because their idea of surplus effectively is increasing utility, but they don't explain how it happens in any real serious way. and they use production functions that say output is a function of technology, labour and capital. And this is the sort of equation they use all the time. Don't worry about the terms so much. Just saying output is some factor of what they call productivity multiplied by the number of workers raised to some power times the number of machines raised to a 1 minus that power. And there's no role for energy in that equation. And when they talk about it, they think, well, energy is just another form of capital. But when a machine is something we make, it's human made, you can't manufacture energy. So to think they can actually make energy, which I've heard some of them say, is nonsense. And their model of how production occurs is just an easy mapping of how they talk about consumption. So they say, well, consumption, you can swap one commodity for another. You can eat less, you drink less beer and drink more wine today. You know, that sort of swapping, easily change around things to get the same level of utility. But it's not inherently wrong to say you can do that. You might say, what amount of utility do I get out of a combination of different goods? And yeah, you might find it hard to compare the two. But in production, yes, you can substitute to some extent labour and capital, but you can't substitute them for energy. Okay? Energy is fundamentally different. And they also talk about perfect efficiency all the time. The idea of perfect this and perfect that, it's just nonsense to say it's all potential. You can't have zero waste in anything in the real world. And then they talk about income distribution reflecting your contribution to production. So they say the wage is the marginal product of labour. It's what the last worker adds. That's what the average wage is. And the return to capital is the marginal product of capital. It's what the last machine adds. And they then say income completely accounts for output. But when you look at energy as well, that's no longer true. You can't account for all output because you're using energy to produce it. You don't pay energy. You pay for energy. You don't pay energy itself. So the whole idea of a marginal product doesn't make any sense at that stage. And you have to do a lot of work to make it work better, particularly their theory that income distribution would have to be ditched. That's a real challenge. Post Keynesians also don't conform, but they don't have this idea of marginal product turning up. So, and they don't say the wage and the profit reflect marginal productivity at all. So they're saying output is a function of labour and capital, which is still wrong, but they don't treat them as smoothly substitutable for one for the other. And just to give you an idea of what that looks like, this is the academic paper I mentioned a moment ago, which happens to be on this topic. And I'll just find, if you look at how neoclassicals talk about the substitutability of factors, then this is showing the amount of output change that's supposed to occur given a change in the amount of each of the factors. And the way they handle energy, they're effectively arguing you can increase energy by a factor of 50% and only have a 2% increase in output. Or energy could fall by 90% and only have a 12% fall in output, which is sheer nonsense. Okay? Where they say a change in labour, if you had a 10% fall in labour, you'd have an 8% fall in output because you'd be substituting machinery and energy for labour. That's not quite so absurd, but energy by far is far more important than their model makes it appear to be. So what you get is a relative bargaining power argument, and that makes more sense. So could you use a carbon price to get rid of the problems of the environment? Well, you can't get rid of this increase in disorder. And if you actually paid for the full price of all the waste you generate, you'd lose money. Think about the example of the turning iron ore and coal into steel. If you had to pay the costs of all the other scrap you create, because you create more crap than uncrap, and more disorder than order, if you asked to pay for the lot, you couldn't. You'd lose money. So in a sense, you have to mine, you have to take advantage of this free gift to have production at all. So it's not possible to price everything and still make a profit because of the laws of thermodynamics. So you can encourage more efficient use of energy, you can encourage less waste, but you can't encourage zero waste, and you can't pay for all the waste, because if you did, there'd be no profit at all. In fact, we'd be making a loss. So there are dilemmas that are given to us by the laws of thermodynamics that are not part of conventional economics. And there's another big problem. The whole idea of a carbon price implies you can set a price on carbon that will stop us damaging the environment. Now, what price on carbon will stop us melting Antarctica? Nobody knows. It's simply impossible to think of that in any sensible way. The price the market sets today can't tell you what's going to happen in the environment 1 or 2 centuries in advance. Okay? There isn't that intelligence amongst ourselves, let alone in the market itself. And one of the most important ones, can we continue growing indefinitely? And ultimately, again, we can't because of the second law of thermodynamics, because you require energy, you necessarily generate waste energy, and that waste alone will limit the possibility for production, even if there was no greenhouse effect. So to actually take energy and put it into useful work, which is the form we want energy to be in, we must actually have this disorder as well. Okay, so there's waste energy and useful energy. Over time, we can actually mathematically measure how much waste energy is produced. And there's a wonderful blog post I recommend taking a read of called Exponential Economist Meets Finite Physicist. And here's a guy with a PhD in physics, a very skilled intellectual physicist, happens to find himself sat next to an economist at a function. And he decided to challenge the economist and see what the economist knew about the laws of thermodynamics. And he started with a claim saying, I believe we can't grow indefinitely. They're limited and they'll prohibit growth within centuries. So literally within more than one lifetime, but not much more than one lifetime, leaving out the greenhouse effect. And he said, oh, no, that's not the case. We can keep on going indefinitely. Energy will never be a limiting factor. Conventional fuels are finite, but we'll substitute non-conventional stuff like tar, like oil, shale gas and stuff like that. And by the time they run out, we'll have renewable energy, and then we're going to have nuclear fission and maybe fusion, and other technologies we can't actually imagine. We're never going to run out of energy. That's the attitude of the economist. And the physicist replies, well, yes, they could. That could happen. But let's look at the amount of energy we're using in terms of the number of watts per year. Now, watts, actually, I should be saying joules per year. But the energy coming out of that light, we measure in watts. You're used to looking at the number of watts for a light bulb. Okay, that sort of thing. So if you plot energy consumption since 1650, and I actually have data going back to 1650 in America on energy, you'll see that's growing at 3% per annum for all that period of time, roughly 3%, very, very close to it. And the whole world is much the same. So this is the chart that he showed for the United States. What he's graphing on the horizontal axis is time. On the vertical axis is the amount of energy production at each point in time. The dots are the actual data for different decades, and then years at the end. That's why the dots get more dense at the end there, and you get this period of what looks like a line. But those are each dots for different decades over time. And a straight line plot fits it pretty damn carefully until the financial crisis, interestingly enough. So that's the data. And they said, how long can we continue that trend? How long can we just keep on going with that level of energy consumption? And his physicist's point was the way that the Earth itself, the entire planet, gets rid of waste is by radiation. Okay? Energy comes in from the sun. Part of it's reflected straight back. Other parts are absorbed by animals and plants and then reflected back with a delay in different forms. Now we know that extremely well, and you can actually measure this, predict what the surface temperature of a planet will be as a function of how much energy we're using on the surface of that planet. And he said if you do that, and you predict that you continue growing at 2.3% real terms per annum, and that's just because if you have a 2.3% rate of growth, every decade you increase the amount of energy you're using by a factor of 10. That's why he used 2.3%. He said if you do that, even without global warming, even without an atmosphere to worry about, the temperature of the planet would exceed the boiling point of water in about 400 years. Now that, in terms of our history, is an extremely short period of time. Okay, that's after Newton. It's something within our own history, within our own sense of time. Within 400 years, the temperature of the planet would boil water. I think you can all understand we couldn't live on that planet. Okay? So, and because global warming actually makes that more accelerated, more exaggerated. So you can't avoid that if you continue using energy on the planet. And if you slow down the rate of growth, then all you do is double how long it takes to get there. So if you slow 2.3 to 1.15, you'll get there in 800 years rather than 400. That's still since the Dark Ages. Make it even slower again, it's since the Romans. It's all within, in terms of looking backwards in time, it's the same perspective we have for recorded historical time. So there's no solution to this apart from getting off the planet, which this guy doesn't discuss. So he said, you simply cannot sustain that rate of growth indefinitely, even if we did get off planet. So he said, in a 2.3% rate of growth, we'd be using energy corresponding to the total solar input striking the planet in 400 years, a bit over 400 years. So at the moment, we're only using it. The amount of energy we actually use on the planet for production is a tiny fraction of the amount of energy that lands from the sun every year in the same time. He said, if we maintain that 2.3% growth rate, then in about 400 years, the amount of energy we're using on the planet will be equivalent to the amount of energy falling on the planet from the sun. And in 1400 years, we'd be using as much energy as the sun itself generates. In 2,500 years, we'd be using the energy of the Milky Way. Now, 2,500 years, we're talking Aristotle, Archimedes, in our own history. Again, extrapolating forward this energy basis says within a period of time, which is our own recorded history, we're doing something which is simply impossible, which is using all the energy of the galaxy we're in. So it simply is unsustainable. And he said we're not going to be doing that. Our rate of growth of use of energy must decline. We must ultimately have at some point in human history, whether that's while we're still on the planet or when we have multi-planet species and so on, even if we create ways to exploit the energy of the sun directly in what are called Dyson spheres, we're not going to be using that much energy. And you can't prevent it with the gains in efficiency either. So ultimately, growth has to end. And that's a physicist's point of view, not somebody like Malthus saying, population growth exceeds growth in agriculture. It's a physicist saying we simply can't do it at that rate. And then we also have the issues of global warming, which is additional retention of heat. So it's not that we're generating the heat so much, we're slowing down how fast it gets away from the planet, and that is adding to temperature overall. Now here is a plot of the amount of carbon dioxide in the atmosphere recorded at a place called Mauna Loa, which is an observatory on an extinct volcano in Hawaii. It was chosen as a basis, I've forgotten Jim's last name, but the guy who was the first person who pointed out the dangers of carbon dioxide in recent history, started recording this back in 1960. And the ups and downs are because of the changes of the seasons, meaning there's more growth of plants in the northern hemisphere than there is in the southern hemisphere. So the northern hemisphere will be more absorption of carbon dioxide when it's summer there than when there's summer in the southern hemisphere. That's the trend we've seen. And a lot of people dispute this. You've got your usual global warming deniers or climate change or climate catastrophe deniers. You can understand, I think you can see what my perspective is on that. But getting through that men's mindset is extremely difficult. So about 30 years ago, I think it was, a PhD student came up with the idea of converting the pressure we're putting on the planet into effectively a measure of how many hectares of land are we each consuming on a daily basis, and how much land does it take to reproduce the resources we're taking out of the planet. He called it the human ecological footprint. And he said, obviously, if you're looking at, say wheat production, and we're eating bread, we can work out how many square metres of land we're exploiting to eat the bread we eat every day. And then you can add in what you consume in, peas, and then you add in animals and so on. That's pretty easy. But he also did the same thing for factories. What's the effective physical land footprint of a factory producing a car for transportation? Map that across as well. And doing all that, he converted the amount of consumption we're doing on a daily basis for every country in the world into a measure of how many acres of land that country is using on a sustainable basis. The planet could actually reproduce that amount. And he reckoned we reached the point where humanity alone, now we're not the only species on the planet. We tend to forget that. Okay? We're not the only species. But just as our species alone, he said in roughly 1970, to consume at the level we are currently consuming at was taking the reproducible resources of the planet that year, every year. So the rest of the animals were eating up their environment. So this is the chart of the ecological footprint of the planet since 1960, and it starts down in 1960 as about 0.75 of the planet's devoted to our consumption in terms of what the planet itself can manage to reproduce. We hit about 1 times the planet in 1970. By the late 2000s and zeros, we're running at about 1.5 times. If we continue doing as we are, by 2050 we'll be using 3 planets per year. We have a problem. We haven't got 3 planets. So the pressure we're putting on the planet's capacity to reproduce itself is immense. And you can actually see this broken down for every country in the world. So I do recommend looking at that website. So we're using about 1.5 sustainable planets per year right now. And forget about global warming in this sense of argument. It's just putting a different metric of the pressure we're putting on the environment. Of course the environment's going to respond somehow to that pressure. So how do we bring all this stuff together? How do we bring economics and ecology together? We have to think about the economy, first of all, in a non-equilibrium world, because equilibrium doesn't make any sense when you're growing. Okay? The vision of a static point just doesn't make any sense. We're moving through time, we're changing over time. And we actually, in terms of what might be described as a planetary equilibrium, where we're adding no more waste than the planet itself can pass into outer space on a daily basis, we're well past that point anyway. We've massively overshot it. And the first attempt to model what are the implications of this was done by a group called the Club of Rome with what's called the Limits to Growth study in 1972. And what they tried to do was model all the ecological and population feedbacks, a very, very stylized way, to see what's going to happen with the combination of the impact of population on pollution, on energy, and this was the sort of thing they'd do. They'd build a flowchart. And I've shown you my flowchart software, Minsky. Okay, Minsky is a derivative of this original research. And what they have is, imagine you wanted to show population growth, where you'd have births per year minus deaths per year is going to be the number of people born per year. And then you'd have the fertility rate telling you how many are born, the mortality rate telling you how many die, and then you feed the fertility rate and the mortality rate, you link those to other things as well. So how many goods are being produced, what level of health care do we have, and so on. That then gives you that particular pattern. Now that's just one tiny part of the entire diagram. Brace yourselves. This is looking more generally. This is population, which I've shown you a moment ago, but depending on how much food there is per head, depending on how much industrial output there is, the pollution coming back and affecting mortality, industrial output depending upon the amount of capital you have. And then when you put the whole thing together, you get something like this. Okay? All the various flows. That's the original diagram of the limits to growth. And again, you can actually download the document. I'd really highly recommend reading that book. It's one of the most neglected books in the history of our understanding of the planet. And this was called system dynamics, which is the approach that I use to economics, which engineers now use, but economists have rubbished it and don't take any particular point. I think economists have ignored one of the most important studies in the history of humanity by doing that. And what they did in this study was say, well, there's 3 possibilities we might reach. You might be able to go from standing way back in the year 0, rising population, and reaching the carrying capacity of the planet. That's what you'd like to do, converge to what the planet can actually support. Another possibility is you overshoot. So you overshoot and you oscillate up and down around the carrying capacity. The least desirable is overshoot and collapse. Okay? You have such an increase in population that you reduce the capacity of the planet to support us, and then you plunge down below it afterwards. So that's the 3 stylized potential outcomes you might have. When they did their standard run, where they said we just basically continue business as usual from 1972, they predicted something like the 3rd outcome. Here is the level of population rising. This is 1900 here, this is 2100 here. So they were predicting a peak for population of about, say, 2050. And they're saying pollution would rise before the whole thing and then collapse. We'd be exhausting our available resources. Food per capita would reach a peak in 2020 or thereabouts and start to fall. A pretty grim vision of where the planet might be. And they said, well, there's other scenarios. For example, what if we have unlimited resources? what you get then is a massive increase in pollution at some point. Okay? So there's feedback effects that mean what looks like a good thing, no limits to the resources, causes another bad thing, far too much pollution, which just delays and changes the nature of the decline. Another possibility was we had things like population control brought in. We started bringing in pollution abatement technology. We started changing across to solar power back in 1975. And they said if we do that, yes, we can have some decline in fixed resources, food per capita stabilises, industrial production stabilises, population stabilises, pollution rises a bit and goes down to low levels. They said if we started changing in 1975, that's the world we could be living in now. Now, unfortunately, we didn't. If we do it too late, if we introduce the same policies sometime later, this is modelling doing it in 2000, they still see a collapse. Of course, we're now talking virtually 2020, and you can see what our politicians are doing about climate change, virtually nothing. Okay, so I think we face a very, very dangerous future. So that's wrapping up the survey of different schools of thought. I'll be talking about different economic issues in the next set of lectures, but how do we actually bring this all together? That's the task which you guys have to work on. I've done some work in it. I'm looking at how you bring energy in, and I want to show you that as a basic idea, because the neoclassical model of production is just involving labour and capital. But they can't exist without energy. Okay? And the little insight that gave me this vision was labour without energy is a corpse. If you find a worker with no energy, he's dead. Okay? And the machine without energy might as well be a sculpture. A blast furnace without energy is just a metal structure with a big hole, with a big solid, a big container in the middle. Okay? A car without energy is a parked car, not going to go anywhere. So you have to have energy. And then when you have the energy, labour and capital harness that energy to make it do useful work. So we eat food and turn those calories into useful work. The machine consumes oil or coal or electricity from nuclear power and turns that into useful work. And GDP itself, the best way to think about GDP is it's useful work. Moving from one point to another when you want to make a movement, that sort of thing. So the proper mathematical form is not to say that you tack energy on the end, but you say labour harnesses energy and so does capital, and convert that energy into useful work. And once you do that, what you're saying is here's the energy coming in, it goes into workers and machines, the workers and machines turn that into useful work, which produces the goods and services we all consume, but waste is necessarily generated as well. So that waste energy can't be avoided. And that's the whole context in which we have to put the whole thing together. And you can drill down and further and say, well, what amount of energy can a worker consume? Well, most of you are consuming less than 4,000 calories a day. If you're burning 4,000 calories a day and you're not getting fat, you're doing a lot of exercise. Okay? And that hasn't changed over time. The amount of available work, you might be consuming 4,000 and doing, say, 2,000 calories of work. That would be a hard working day. That hasn't changed over time either. And these days, rather than doing direct work, we're controlling machines. Rather than hitting with a sledgehammer, we're using a jackhammer to make the holes. And then there's efficiency. How efficiently do we work? And then you look at a machine. Well, how much energy does a machine consume? Well, if you go back and look at the Watt steam engine, that consumed about 10 tonnes of coal per day. If you look at Elon Musk's rockets, they consume about 10 tonnes of fuel per second. That's about a 25,000 times increase in the amount of energy. And that's how we've got the increase in productivity that we see these days. Now, maybe 70% that's available, maybe 50% efficiency. That again is changing over time. If you imagine Musk's idea of a hyperloop for transportation, that is much more efficient than a car because there's no friction, virtually no friction, okay, because it's running inside a vacuum tube and so on. So more efficiency, but we can never get that perfect productivity. If you look at workers, you go back and look at a Roman slave, then that's directly using human energy to do work. And the machine is, a shovel or a sledgehammer to do the work. Look at a modern human, the worker's pressing buttons. So the calorie output of the worker is pretty trivial. It doesn't really matter. But machines, you look at a Watt steam engine, yeah, they could move with a small amount of energy. Where we are today, much, much more energy. So it's the usage of the energy that's actually made us much, much wealthier than our forebears were. So I cover a bit more of that. There's a technical paper I've linked there if anybody wants to have a look at it. So it's possible to bring this stuff in, but it completely changes the nature of economics. Unless we do it, we won't have an economy. Okay, leave you with that thought. Back to your essays, and see you next 2 weeks' time.